standard Young tableau of bounded height and non-crossing and non-nesting involutions. And I'm gonna tell you a little bit more about cylindric tableau and cylindric Schur functions. And I'm going to tell you our main results and original motivation of our work. And actually, this is our main result, Affine Gordon-Bender-Knuth identities. I will explain what these identities are almost at the end of my talk. Okay, so let's begin with basic definitions. So a partition of N is a non-increasing sequence of positive integers summing to N. As usual, we denote the length of lambda in this way, and each element in a partition is called a part. So this is basically the number of parts. And the Young diagram of a partition is drawn by these left justified squares, so that ith row has lambda I. For example, if lambda is 552, we have the Young diagram that looks like this. And the standard Young tableau of shape lambda is a filling of these cells or squares of the Young diagram with integers 1 up to the size of lambda, so that integers are increasing each row and in each column like this. And a semi-standard Young tableau, or also called column strict Young tableau, is defined similarly, but we may have repeated integers, or some integers may be missing as well. And integers are weakly increasing in each row and strictly increasing each column. And row strict tableau is defined exactly the same way, except that the strict inequality along columns now becomes strict inequalities along rows. All right, so basic definitions. I'm sure that these will be used throughout this workshop. Okay, so the Robinson-Shenstedt algorithm is a very well-known algorithm in combinatorics and representation theory that gives a bijection between permutations of N and pairs of standard Young tableau of the same size or the same shape. By the way, yeah, I mentioned that the shape is lambda. So this is the bijection is between permutations and pairs of standard Young tableau of the same shape, like I wrote here. And I'm not going to give you the precise definition of the map because it's very well known. You can find this in any standard textbook in combinatorics, like Stanley's enumerative combinatorics. So, for instance, if you have a permutation like this, the Robinson-Shenstedt algorithm gives us a pair of standard Young tableau of the same shape. In this case, the shape is 3, 2, 1. And the algorithm breaks down into what's called the insertion algorithm, but yeah, I'm gonna omit the details. And there are many interesting properties of the Robinson-Shenstedt algorithm. One of them is the following: if permutation corresponds to the pair P and Q, then its inverse corresponds to Q and P. So if the permutation is an involution, meaning that the square is the identity, then we have the pair is just P and P. So we can just think of this as a single tableau. So this gives us this result that involutions of N are in bijection with a standard Young tableau of size N. And there are several ways of looking at involutions, and we will consider these matchings. So an involution is a permutation such that every cycle is either a length 1 or length 2. So length 1 cycle means just a fixed point. So if permutation has just 2 cycles of length 2, 2, 6, and 3, 4, then we can represent this as a matching in this way. So singleton or fixed point means that it is fixed by this permutation. And 2, 3, 2, 6, if this form of 2 cycle, we connect the 2 dots like this. And this is the permutation in the 2-line notation written in this way. So an involution is really a matching if you look at this bijection. So RS correspondence can be seen as a bijection between involutions and or matchings and standard Young tableau of size n. And now let's consider standard Young tableau with bounded height, where the height of a standard Young tableau means just the number of rows. So for example, in this standard Young tableau, the height is 3, which is the number of rows. And I'm going to denote SYT sub n, the set of standard Young tableau of size n. And this means that the height is less than or equal to h. So height is at most h. And for small h, the cardinality of this set has a nice description. For example, h equals 2, this is the central binomial coefficient. And if h equals 3 is the number of Marchkin path of length n, and h equals 4 is the product of 2 Carolan numbers. But if h is bigger than 4, it's not as simple as this. But Gessel found this nice generating function formula for the standard Young tableau with bounded height. So where here is a determinant on the right-hand side of difference of what's called a modified Bessel function. And I only wrote the even odd case, but the even case is also known. Okay. And now I'm going to review some more properties of the Robinson's algorithm. I already mentioned that if pi corresponds to PQ, its inverse corresponds to QP. And the maximum length of decreasing subsequence is equal to the height of P, or number of rows, or maximum length of increasing subsequence of pi is the width of P, or the number of columns. For example, this corresponds to the pair P and Q. And you can see the maximum decreasing subsequences. There could be many, but 4, 3, 2 is one of them. This is the maximum possible, and the length is 3. And you can see that's the number of rows, like this. And the maximum increasing subsequence is 4, 5, 6, 7. And you can see this the size is 4, which is the number of columns or the width of this permutation tableau. Okay. Now, if you combine these properties that I mentioned, then we can conclude the following. So involutions are in bijection with standard Young tableau. And involutions are really just matchings. So involutions with no k nesting is, what I mean by this is a k nesting is k arcs, a set of k arcs, such that any 2 of them are nested each other like this. So this is a 3 nesting. So if there are k arcs, such that one is nested by any of them, then it's called k nesting. And you can see if we have a k nesting in this involution or matching, then in the corresponding involution, there should be 2k decreasing subsequence of length 2k. For example, here, if you look at this, then you see this corresponding involution looks like this. And this is really 6 and 2 in the one-line notation, and 4 and 3. As you can see, these 4 numbers are decreasing. So whenever you see a k nesting in the matching, then the corresponding involution has a decreasing subsequence of length 2k. So, and by the RS algorithm, here we have standard Young tableau of size n, and the maximum length of the decreasing subsequence corresponds to the height. So there are no k nestings, means that standard Young tableau has height less than 2k. Okay. And now, so this is one thing, but when we have nestings in a matching, the natural counterpart is crossing. So an involution or matching is, we say, R non-crossing if it has no R edges crossing each other like this. And we say that an involution is S non-nesting if it does not have S arcs nesting each other like this. And let me denote by NCNN R, S, the set of R non-crossing and S non-nesting involution. That means we only consider involutions of N that does not have R crossing nor not S nesting. And there is a nice symmetry between these nestings and crossings due to these people. They prove this in a very nice way using RSK. And in particular, if you just consider, maybe you can say S equals infinity, for instance, then this gives us this relation. The number of k non-crossing involutions equals the number of k non-nesting involutions. Okay, now we have non-crossing and non-nesting, these two statistics. Natural question can be asked as follows. So here's a summary of what I have said so far. The number of standard Young tableau of size n with height bounded by this 2k plus 1 is equal to the number of k plus 1 non-nesting involutions of n. This is due to the map, the Robinson-Shenstein bijection. And because of the symmetry between nesting and crossing, this number is equal to k plus 1 non-crossing involution. And we also have a very simple symmetry about this standard Young tableau, namely just if you take the transpose of the tableau, which means that you reflect the tableau about this diagonal line, then you get another standard Young tableau. And of course, the rows now become columns. So standard Young tableau with height, bounded height equals standard Young tableau with the same bounded width. So now we have these four objects all counted by the same number: standard Young tableau with bounded height, standard Young tableau with bounded width, and non-nesting involutions and non-crossing involution. They're all equal. And so the natural question is, can we combine the two statistics together and so that we still have the same identity? So for example, the question is are these two numbers equal? The standard Young tableau of size n with bounded height, 2h plus 1, and bounded width, 2w plus 1. Is this number equal to the number of h plus 1 non-nesting, w plus 1 non-crossing involution? And if you think about this a little bit, you will realize that the answer is no. Because imagine that, just think about this left-hand side. We have standard Young tableau with bounded height. So this is bounded, and width is also bounded. Then the number of cells can be at most this times this. So if n is bigger than the product of these two numbers, then this is always 0. But on the other hand, the right-hand side is never 0 because the identity involution, identity permutation is always non-nesting and non-crossing for any h and w. So these two cannot be the same. So so the next question would be, can we find kind of a nice subset here so that this is really equal to the one that we count over here? All right, so then we found such a subclass of standard Young tableau, and they are what's called cylindric standard Young tableau. So let me define what they are. So for fixed integers h and w, HW cylindric semi-standard Young tableau is a semi-standard Young tableau such that the height is first of all bounded by h, and we have to have this second condition. So this is our semi-standard Young tableau T. Now I make a copy of this and shift this down by h and to the left by w, and then attach the copy over here. Okay. Now, if this is a semi-standard Young tableau of a valid skew shape, then we say there's HW cylindric. The semi-standard means that integers are increasing, weakly increasing each row, strictly increasing each column. All right, so let me give you an example. So this is a semi-standard Young tableau, and this is 3-3 cylindric because I shift this by down by 3 and to the left by 3. Then the resulting diagram looks like this. It's a valid skew shape. And integers are increasing in each row. These are by definition of T. And we only need to look at the columns with the overlapping elements or cells. So here, it's still strictly increasing. So this is cylindric. But this is not 3-2 cylindric because I shift this by 3 and 2. Then as you can see, this is not strictly increasing. So this is not 3-2 cylindric. And this is not 3-1 cylindric either because you don't, now in this case, you don't even have to look at the entries. If you shift this 3 and 1, then you can see this is not a valid skew shape. By the way, I don't think I defined skew shape, but skew shape is a set theoretic difference between two partitions like this. All right, so now we have this object. By the way, cylindric tableau have been studied before our work. First, they were studied by Gessel and Kratanteller, and also by Postnikov and other people. I'm going to tell you more about the history of the cylindric object later in my talk. And a cylindric, I only define SSYT, but you know the idea. A cylindric standard Young tableau is defined exactly the same way. Okay, now let me define this set. CSYT HW is a set of all HW cylindric standard Young tableau of size n. And our theorem is this. The question answering this, the answer for this question is this. This is the right object to that should be counted by the same as this non-crossing non-nesting. So non-crossing non-nesting for this H and W is the same cardinality as the cylindric standard Young tableau. It's this comma this cylindric, I mean. For example, if n equals 4, h and w both equal to 1, then let's count both sets. Or let's count those that are not cylindric or non-crossing non-nesting. For example, here, there are two standard Young tableau not counted by this set. Namely, this standard Young tableau and this. Because if h equals 1, this is 3, so height must be, you can see this is not like, you know the idea, right? So we have these two examples that are not counted by this, but for non-crossing non-nesting, if h equals 1 and w equals 1, and this, we have two involution not counted by this, because this is two crossing, this is two nesting. This must have like two non-crossing and two non-nesting. So that kind of tells us the the case for this when h equals 1, w equals 1, n equals 4. And I'm going to give you a brief outline of the proof, but the thing is, the proof is not bijective at all. So an open problem that I would like to suggest is to find a bijective proof of this result. Because everything is purely combinatorial, I think there should be a nice bijective proof of this. Okay, but before telling you the proof, I'm gonna tell you this original motivation of our work. So in 2015, Mortimer and Prellberg, they found a very nice identity between two combinatorial objects. On one side, we have Mochkin path with a bounded height. So Mochkin path is a lattice path from 0 to 0 to n comma 0, consisting of up step 1 comma 1, horizontal step 1 comma 0, and down step 1 comma minus 1, such that that stays in the first quadrant. And the height is of the Mochkin path is the maximum y coordinate of the points in this path. So in this case, the height is 2 because the height of this point, the y coordinate is 2. So we can think of all such Mochkin path with bounded height in this case 2. And on the other side, let's look at this triangular lattice of size k. That means that we have this triangle divided into like smaller triangles of size 1. And here the number of sides that in the last row is the size of this triangular lattice. And we have 3 possible steps, this step and this step and this step. And we start from this corner and consider all lattice walk consisting of these 3 steps, but the ending point can be anywhere. So they showed, Mortimer and Prellberg showed that the number of Mochkin path of length n with height bounded by w equals the number of lattice walk of length n in this triangular lattice from 0 to anywhere with bounded this triangular lattice. For example, n equals 3, w equals 1, we have the height must be less than or equal to 1, so we cannot go beyond this line. There are 4 such Mochkin paths, and there are also 4 lattice walk in this triangular lattice. So 1 is this, 1, so step 1, 2, 3, or you can go this way, or this way, or this way. There are 4 of them. So they are equal. So again, very simple combinatorial objects being counted by the same number. But again, their proof was not combinatorial. They used generating functions and the corner method. So we first, in our original motivation, we wanted to find a bijective proof of this result. Oh, sorry about that. Okay. So now we will change these problems into the problems that in our main theorem that looks more like in our main theorem. So first, Mochkin path can be easily transformed into non-crossing matchings. So whenever you see an up-step, you have a half open arc, and this corresponds to a fixed points, and half open arc, this half closed arc, etc. And then you connect the half edges so that there are no crossings. There's only one way, so it's 2 crossing. And the height here corresponds to the fact that there are no w plus 1 nesting. So this is basically, this object is basically the same as 2 non-crossing and W plus 1 non-nesting involutions. And on the other side, walks in this triangular region can be turned into a sequence of partitions. And whenever you see a step, east step, we begin with an empty cells, and we add a cell in row 1 in the Young diagram. And for this step, we add a cell in row 2, and for this step, we add a cell in row 3. For example, this lattice walk like this can be turned into a sequence of partitions like this. But in each step, we added one cell. So this can be naturally encoded as a standard Young tableau like this. So first cell is written here, it's added, and the second cell is added here, and third cell added here, etc. So you can see it's just a standard Young tableau. And the condition that this standard Young tableau came from such a process corresponds to the fact that this standard Young tableau is 3, 2W plus 1 cylindric standard Young tableau. For example, this, in this case, W equals 1, I think. So we shift this 3 and 3, then we get this, and you can see it's still increasing. So it's a standard Young tableau, a cylindric standard Young tableau. So this side is really the same as a cylindric standard Young tableau. And this observation was also found by Elizalde independently. Okay, so now we can rewrite their theorem in this way. The Mortimer-Prevost result is equivalent to this identity. I mean, the cardinality of these two sets. Non-crossing, 2 non-crossing, W plus 1 non-nesting, and 3, 2, 8, W plus 1 cylindric. So we first found this description, and we checked by computer that maybe if you can replace this by another parameter, then we still have the same identity. But yeah, the answer is yes. That's how we discovered this theorem, and our theorem has this Mortimer and Prevost result as a special case, namely H equals 1. And by the way, our original motivation was to prove this bijectively, which we couldn't. But recently, these people found the bijective proof of the Mortimer and Prevost result. But the general case, the finding of bijective proof is still open. Okay, so this is our theorem, and the idea of the proof is like this. We express each side as the number of lattice walks, and we express the number of lattice walks using the generating function using determinants. And after that, all we need to do is to prove this one big determinantal identity. And that's how we proved it. So to explain this idea, I think we need some definitions. So first, a cylindric Young tableau is, after all, a standard Young tableau. So it can be written as a sequence of Young diagram, just like we saw 2 slides before. And this, because partition is just a sequence of numbers, it's just, we can think of this as sequence of points in R3. So this is basically a walk in the region. Because it's partition, it has to be weakly decreasing. So it has to be like this with step 3 steps like this. Because in each step, we add 1 cell in 1 row. Then under this correspondence, this cylindric standard Young tableau corresponds to walks in this region. with additional condition like this. This came from the condition that this tableau is cylindric. And if you we can write this in one row like this, and this turns out to be the alcove of an affine Wire group of type AN. So this is basically counting walks in an alcove. And the other side, for the other side, we need this object called a vacillating tableau. So this is again a sequence of partitions, but it starts from the empty partition and ends with the empty partition. And each is two consecutive partitions differ by at most one cell. So it may be we can either add one cell or delete one cell, or the two consecutive partitions could be the same, just like this. And there is a well-known bijection between involutions and vacillating tableau of length n. And if you consider, I told you involutions are basically matchings. So non-crossing, H+1 non-crossing, W+1 non-nesting involutions under this bijection correspond to a very nice and simple condition on the vacillating tableau, namely every partition is contained in this box. So again, this can be understood as a sequence of partition, which is again just a lattice walk. And the bijection is well known and is basically kind of using RSK, but I'm gonna omit the details for to save time. So these non-crossing and non-nesting involutions are in bijection with vacillating tableau with each partition contained in this box. And like I said, so just a number of that they are just a lattice walk in this region with some steps. And it turns out that, again, this is an alcove of an affine Wire group, but with a different type, C. So both sides are just a lattice walk in an alcove. And there are known results by Filaceta. He computed the lattice walk in an alcove, in an affine Wire group, and applying his result, we can get a formula for this and also the generating function for this. So basically, we have generating function for both sides. So, so our theorem, our result is equivalent to this identity, generating function identity. The generating function, right. But in fact, we will prove multivariate generalization of this result we will turn this into symmetric function versions. And okay, so I guess we need to define some terminology again. So Schur function is the generating function for semi-standard Young tableau. For each semi-standard Young tableau, we add the monomial x1 to the number of ones, x2 to the number of twos, etc. So for example, this gives us x1 squared, x2, this gives us x1, x2 squared, etc. And you can see if you extract the coefficient x1 up to xn in this Schur function, then we get the number of semi-standard Young tableau. So this is why when we have a result on semi-standard Young tableau, we can also mostly get the result on corresponding standard Young tableau. Okay, and Schur functions are well-known basis in the symmetric function space, and there are two also important bases in the symmetric function, namely complete homogeneous symmetric functions and elementary symmetric functions. So we can write Schur functions in terms of homogeneous or in terms of elementary. here I use this notation transpose, lambda transpose, which is the Young diagram obtained by transposing the diagram about this diagonal. And so these are called Jacobi-Trudy formulas. And Gordon-Bender-Knuth identity is an identity for the sum of all Schur functions with fixed bounded width or equivalently bounded height. And for our purpose, it's more convenient to work with lambda prime. So I'm going to write their identities in this way. The sum over all semi-standard Young tableau or Schur functions with bounded height, but we take the prime, the transpose. So you can think of this as the generating function for all semi-standard Young tableau with bounded width. And this is written in this way, where this is the elementary symmetric function, and f is the sum of the product of two elementary symmetric functions where their indices have the same difference. Okay, now we're gonna find a fine version of this theorem. That will give us the results that I told you. And to do this, it's more convenient to use row-strict tableau. I already mentioned this. And cylindric row-strict tableau can be defined exactly the same way. Row-strict, but we shift h by down by h to the left by w. We still have the same condition, like the row-strict condition like that. It is called HW cylindric row-strict tableau. And I'm gonna define this set of all HW cylindric row-strict tableau of shape lambda. Okay, then this is the Jacobi-Trudy formula for the cylindric Schur function. By the way, what I mean by the cylindric Schur function is just like the Schur function, it's the sum of all generating function for cylindric semi-standard Young tableau or equivalently row-strict tableau. So this you should think of this as the cylindric Schur function, and we have Jacobi-Trudy-like formula for this cylindric Schur function. And before stating our result on this affine version of this, let me first briefly tell you about the history of the cylindric tableau. So cylindric tableau or equivalently cylindric plane partitions have been first studied by Gessel and Kratanteller, and they found the formula for the generating function for the cylindric plane partitions, and they found some connection with AR tilde basic hypergeometric series. And these people, they show that quantum Koska number can be expressed using certain cylindric semi-standard Young tableau. And Postnikov showed that cylindric skew-Schur function of some condition called toric shape with bounded number of variables equals can be written in terms of Schur functions, and the coefficient is the 3-point Gromov-Witten invariant. And from this, we can see that under this condition, it is Schur positive. But this is no longer true if the number of variables is infinite. In fact, McNamara showed that cylindric skew-Schur function, if it's not a Schur function, it actually contains a Schur function. So a genuine cylindric skew-Schur functions are not Schur positive if there are infinitely many variables. But he conjectured that cylindric skew-Schur function is skew-Schur positive. Actually, skew-Schur functions are do not form a basis, but we have to have some condition that we only look at skew-Schur functions contained in certain rectangle, in that case, we have a basis, and this was conjectured by McNamara, and Seung-Jin Lee proved his result. So cylindric standard Young tableau and semi-standard Young tableau have been studied previously by these people. Okay, now let me tell you our main result. So the Gordon-Bender-Knuth identity is basically saying that the generating function for row strict tableau with bounded height equals some determinants. And our main result is the affine version of this. So this is the sum of cylindric Schur function. So, or combinatorially, the sum of all cylindric 2h plus 1 comma w cylindric row strict tableau equals similar sum of determinants. And if this, our result is a generalization of the Gordon-Bender-Knuth identity, in the sense that if W approaches infinity, and that means the cylindric condition just disappears, because W, you shift H by H down and W to the left by W, but if W equals infinity, we don't have any overlaps, so it's just a row strict tableau with bounded height. So it reduces, this reduces to this, and also here, if W equals infinity, everything here has to be 0. So we get exactly the right-hand side of in this identity. And we also have the odd even version as well. And yeah, here's the outline of the proof. We first of all, we have a Jacobi-Trulli formula for given for the generating function for cylindric row strict tableau with fixed shape. So you can use that Jacobi-Trulli formula, and the left-hand side can be written in this way, where because we don't really fix the shape here, only we have the condition that number of rows is bounded. So we have sum over all partitions like this, and we can instead of this, we can rewrite using so the idea is here the integers are sorted by their sizes, but we sort the integers by their remainders when divided by some integer n. So this is rewritten in this way, and we were, so the identity is just equivalent to this, and we were able to turn this determinant, the sum of this determinant, into a single Pfaffian, and we were able to evaluate the Pfaffian using known result and techniques in the Pfaffian and determinants. So that's how we basically we prove the identity. But again, it's not combinatorial, so finding a combinatorial proof would be very interesting. Now, let me tell you a little bit of the consequences. So because here, in this identity, by extracting coefficients of x1 up to xn, we can get the number of standard Young tableau with conditions being cylindric. So in that case, depending on the parity of H and W, we get these 4 identities. So this is the thing that I told you at the beginning of my talk. All right. By the way, if you look at this, we have W plus half, non-crossing or non-nesting, but this half means that instead of looking at this arc, we also include a fixed point like this. So technical definition is omitted, but the idea is like that. And if H equals 1, these 2 identities become Mortimer and Prellberg's result. And if H equals 1, these 2 identities identities become some non-trivial identities on the number of lattice path on with some conditions. I'm not gonna give you the details. So the idea is, I mean, the thing is, this we have bijective proof for h equals 1, but for general h, we don't have any bijective proof of this. So I guess I can tell you some open problems. First of all, find the bijective proof of these results that that we got using the affine Gordon-Bender-Knuth identities. And we have generating function for all of this, but when these two are like both half integers, we don't have a generating functions. So for finding a generating function for this object is also an open problem. And also the last one is, unlike these three, we have a less satisfying answer here because it's kind of signed sum with some statistic. So it will be interesting to find a sign-free expression for this identity. By the way, if you replace this by this, that's not going to be true. So it's not really exact the same form. So we have to define something else. And I guess that's all I wanted to say. Thank you for your attention.
Okay, is there any question or comment? I have one. So when you talk about the history of cylindric standard tableau, you mentioned that so the Namarra's conjecture is cylindric Schur functions are cylindric Schur positive or Schur positive?
Schur positive. Schur positive.
Because I'm a bit confused because Schur functions are Schur positive, right?
You sounds right. Maybe Seung-Jin can answer. Did I say something wrong?
Yeah, conjecture was the cylindric Schur is cylindric Schur positive.
Okay.
Cylindric Schur. Oh, okay. Thank you for the correction. Okay, cylindric. Okay, yeah. Yeah, thank you. Yeah.
And have you ever considered? I have one more question. Have you ever considered some? There is some operations like promotion or evacuations in standard tableau. Is there a generalization to cylindric objects, and if we can translate into lattice path or something?
That I don't know, and I don't think much of the work have been done on combinatorially on cylindric standard Young tableaus. So I think if you can do generalize many interesting things in known for standard Young tableau or semi-standard Young tableau to cylindric object, I think it would be very interesting.
Thank you. Is there any questions? If not, let's thank to the speaker again, and we'll resume at 10. Depends where you are. And Anna, can you share your screen and test your slides?
Yeah. Can you hear me though?
Yeah.
Okay, cool.